Okay, Nandi. Good morning, dear students. Welcome to the second day of GATE classes. It is a wonderful opportunity to you. The JNT of Anantapur is arranged this particular the third phase of GATE coaching. I hope we are happy with the classes. Today, yesterday, let us what we have discussed. We will brief once. What are the fundamentals are required, the prerequisite subjects required to understand this subject like physics, mathematics and other things which we have discussed. And some of the concepts like what are the assumptions for a system and subject wise what are the assumptions like engineering, similarly engineering mechanics, what are the assumptions which we have considered. If you go through, this is basically more or less the same syllabus for mechanical as well as civil engineering students. See, in this particular syllabus, yesterday we have concentrated system of forces, free body diagram, equilibrium equation, something we have started yesterday. And today I am mostly concentrate on the equilibrium equations and these the free body diagram, system of forces, how to analyze the particular problems. And for different like one-dimensional, two-dimensional, three-dimensional problems, how to represent equilibrium equations for any system. And some principles also yesterday we discussed like principle of transmissibility, the principle of superposition, some graphical methods like some polygon principle, equilibrium, that is the triangular law of principle and parallelogram law and Lami's theorem, etc. and some basic and derived fundamental quantities, units, etc. See, that is basically what we have covered yesterday. See, today I am going to touch mainly the equilibrium equation, then we try to solve some problems by considering the system of forces, free body diagrams, equilibrium equations. These are the things which we are going to, more or less the syllabus both are same. That's why today we will try to complete this part of the syllabus. See, what are the learning outcomes from these three topics, that is the system of forces, free body diagrams, equilibrium equations, if you can recollect. Because nowadays, whatever you are learning, what is the outcome of that? Then what we are calling as an outcome-based education, where it is useful. If you can quickly look into that, these are the learning outcomes. So if you want to write an equilibrium equation, we need a system of forces, we need a free body diagram, we need the input of the data, how the input is given. Here, the given system, you have to express or represent either 1D or a 2D and 3D equilibrium equation. From 2D you can convert 1D basically, that's why I have not mentioned that. You represent your or express your equation in the form of 2D or 3D equilibrium equations. By using, then recognize and apply the concepts of these equilibrium to the physical real system. Before applying, you have to consider what are the system of forces by representing a free body diagram. Then explain the relation between the sum of the forces and moments. Is there any relation between these concepts? See, these are the concepts every student has to understand these are the learning outcomes of these three topics. Updating your knowledge as per this course based on the need, and this will be useful in other future subjects like design, theory of machines, in case of civil engineering, strength of materials, mechanics of materials, and finite element analysis, etc. We will use this particular subject. That is what is the future subject which we are going to apply these concepts. Okay, so these are the learning outcomes from the yesterday class and the today class. The student what they are going to get by using the Bloom's taxonomy. You can lower level or higher order level, both the cases this subject will come. And by keeping this in mind, now let us go to the today topic, that is equilibrium equations. Here yesterday we have mentioned we try to consider the first and foremost point is what is the degree of freedom of system which we are solving. You have to define first based on the given conditions. That is the first point of yesterday also I defined that. If you want, you can note down. The degree of freedom is defined as the number of independent coordinates which are required to specify the position of a rigid body or any body. But here is a rigid body. Once again I am repeating, the degree of freedom is defined as the number of independent coordinates which are required to specify the position of a rigid body or any system. That means, see, when we are doing something, when we are analyzing a system, that system is having how many degrees of freedom. Without knowing the degree of freedom, we cannot solve the problem. That's the basic thing. So that's why you have to see what is the degree of freedom. The simple logic is, if the degree of freedom, when I am teaching, if I want to erase the blackboard, yesterday also I give an example. The duster, if you can represent with some coordinate system, the degree of freedom is always representing with some coordinate system, like rectangular coordinate system, polar coordinate system, cylindrical, spherical, etc. You take any coordinate system depending upon the condition of the problem. Suppose the duster is moving on, I am considering a rectangular coordinates. The length is x and the width is y, and it is a rotation. So now, when the duster is moving, like it is in a three-dimensional the rectangular shape base, if you can extrude, it will form like a duster shape. With that, if I want to erase on a blackboard, it can move in x, it can move in y, and it can rotate also. That means that system is having two translations and rotation. What I want to say is, the degree of freedom is always defined with number of translations and number of rotations. That is what is the first two statements. With respect to translations, what are the sum of the forces acting on a body? Is it equal to 0? If it is 0, it is equilibrium, otherwise it is not an equilibrium. That is what the philosophy. So that's the first and foremost point. What is the translation degree of freedom of your system? And similarly, what is the rotational degree of freedom? The second statement says that the sum of the moment about any axis must be 0. These are the two things which we have to define. That number may vary. Maybe 2 translation, 1 rotation, 1 translation, 2 rotation, or 3 rotations, or 3 translation, 3 rotations, or 2 translations, 3 rotations. Because we are considering a single rigid body, the maximum degree of freedom is 6 in a space. In a planar, it is a 3. Because of that, you take any combinations. Suppose let us take as a mechanical engineering or a civil engineering, simple example, IC engine mechanic. Please try to concentrate very carefully here. You know very well the IC engine mechanism, that's why I am not giving a sketch here. IC engine mechanism consists of cylinder like your scooter also. The engine what we are using is internal combustion engine. In that piston is there, cylinder is there, connecting rod is there, crankshaft is there. Cylinder is fixed. The piston is moving forward and backward. That means a translation degree of freedom. It is the degree of freedom of piston is moving. Let us assume it is moving in a plane. If you want, you can move in a space also. Let us assume in a plane, it is moving forward and backward. With respect to origin, whether you are moving a positive or a negative, that is the coordinates only, but it is a 1 degree of freedom. You take the crankshaft. The crankshaft is with shaft as an axis, it is rotating. It is a rotational degree of freedom. That means only we are getting one. That rigid body is concerned. If you are considering a crankshaft as a rigid body, the degree of freedom is a rotation. If you are considering piston as a rigid body, you have a translation. Now connecting rod is connecting between the piston and the crankshaft. One end of the piston, one end is piston. Piston is a translation. And the other end is a crankshaft. It is a rotation. That's why the connecting rod must and should consist of 2 degrees of freedom. One is a translation, the other is a rotation. See, this is how, that means as an individual rigid body, we can define the degree of freedom system. As a whole system also, like a crankshaft mechanism or a machine or any structure, we can define what is the degree of freedom of the system in terms of number of translations and number of rotations. Whereas in our subject, we are considering the number of forces, number of moments. Some of the forces 0, some of the moment 0. These are the 2 basic necessary conditions of an equilibrium equations with respect to the degree of freedom. When the dust is moving on a blackboard, X translation is possible, Y, because the duster has to erase the topic what I have written on the board. It should be always in contact with the plane surface. A plane is nothing but 2-dimensional thickness. The blackboard length and width, compared with length and width, thickness is negligible. See, that's why it is a 2-dimensional. It is a planar system. If it is a 3-dimensional, it is a spatial system. That is the difference with respect to coordinate system. Thickness is negligible for a board. I am considering as a 2D. See, that's why it is having X translation is possible, duster, Y translation is possible. The rotation about duster also you can arrange it. That's why 2 translations and 1 rotation is possible. See, this is how we will consider the equation, equilibrium equation. Then, or you can take another example. I am moving on the X. I can move on X, I can move on Y, and then I can rotate about my vertical axis, that is the Z axis. Again, it is having 3 degrees of freedom. If I throw a chalk piece from the dais to somewhere, it is having X translation, Y translation, Z translation. When I am from throwing point to reaching point, it won't occupy the same position. It is having different orientations. See, that is the reason why it is having X rotation, Y rotation, and Z rotation. So this is how we will try to represent a system by considering number of translations, number of rotations, and try to analyze the system. See, by considering this, what are the number of forces in equilibrium and number of moments we have to equate with 0. This is what is the equilibrium, the concepts of equilibrium. Now these two conditions are necessary and sufficient conditions. We cannot satisfy with one, both has to satisfy. The first condition is necessary because it must and should satisfy, otherwise it will result in inequilibrium in terms of rotation. It satisfies the translation but it is not satisfied the rotation. Similarly, the second condition, if it is fulfilled, it is not satisfied the translation. That's why the two statements must and should satisfy for any system to keep in equilibrium. This is a thumb rule you have to keep in mind. The two conditions are sufficient because of equilibrium without the need of any additional conditions. Now, depend upon the system, you have to consider the number may vary now, but number of translation, number of rotation. See, this is what is called the concept of an equilibrium. I hope you got the clarity. I give a number of examples. Or let us take for civil engineering point of view, I am considering the bar, beam and even truss and frame, 4 structures we can consider. Bar is a one-dimensional. Bar means it is a axial member. I can apply a tensile load or a compressive load. Like a truss member also indirectly a bar, but we are keeping in some orientation also, considering orientation. Whereas bar is always we keep either X, Y, Z. A truss is not only that, you can keep an inclined orientation, any orientation also. That is the basic difference between the bar and truss. The beam, that means it is having only 1 degree of freedom. The increase in length or decrease in length, tensile member or compressive member. It is there in our topic also, we are going to discuss in the next class, the trusses. Let us consider beam. When you apply a load, the beam is having a translation degree of freedom and rotation degree of freedom. The translation is purely, that is shear force, and rotation is a bending moment. That is having a 2 degree of freedom as a body. If you take more number of rigid bodies, then the concept is different. As a single rigid body, you have a translation and rotation degree. Or a frame. In a 2D only I am talking. If it is a 3D, again it is changing. I am assuming as a 2-dimensional. It is a planar system. If it is a 3D, it consists of three translations and 3 rotations. Same beam or same bar or same frame. But that number depends upon the type of structure, the number of degree of freedom is varying. If it is a frame problem, let us 2D. X translation is there, Y translation is there, Z rotation is also there. All 3 degree of freedom we are getting. See, that is how a mechanical system or a civil engineering system, we have to define the degree of freedom of a system, then apply the equilibrium equations. See, this is how generally the analogy what we are adapting to write the equilibrium equations. You know, some more concepts are, that's what I already mentioned. The first point is the resultant force vector for planar force system in the plane of action of a original force system, that is in a plane actually it is, on a plane, PLAN. The resultant moment vector, that is force vector acting along the plane, moment vector acting perpendicular to that plane. That is what is the difference, one more difference. And it can be considered a planar system as well as the spatial system. Planar is basically 3 degree of freedom, spatial basically 6 degree of freedom for a rigid body. The equilibrium concepts are generally applicable for stationary or moving with a constant velocity. That means it is indirectly in Newton's second law. No, Newton's first law, basically, sorry. Newton's first law says that every body in the state of rest or maybe uniform motion unless there is no external force acting on a body. Here also the equilibrium condition also same. The concept of equilibrium is introduced to describe a body which is stationary or which is moving the condition is with a constant velocity. The Newton's first law says that every body in the state of rest or maybe uniform motion. Uniform motion means constant velocity. There is no acceleration. A body under such a state acted upon by the balanced forces and balanced couple. There is no question of unbalanced. Equilibrium means there is no resultant force or resultant movement. It consists of force and couple. A body under such a state is acted upon by the forces and couples. If there is an unbalanced force, unbalanced scope, then there is no question of equilibrium. It comes under dynamics. The first one is statics, and the second one is the dynamics. So that means in our statics, now we are considering statics part, later stage we will consider the dynamics. The concept of equilibrium is used to analyze the system under stationary, or in other words, static equilibrium. That is what is the static analysis. See, with this introduction, only I given the introduction of why we have to, when we will consider the equilibrium equation, that the concept of degree of freedom. Suppose I will give two more examples, with that I will close this introduction. Instead of duster, like in a three-dimensional rectangular cuboid shape, now I am considering a chalk piece like a cylinder. I am writing a chalk piece on the blackboard. The chalk piece is a cylinder shape. Let us assume. When you write with a cylinder shape, it is having X translation, it is having Y translation. On a plane only I am writing. But the chalk piece is having the Z rotation perpendicular to the blackboard. That is having a 3 degree of freedom. That is what is the plane. X translation, Y translation, chalk piece can I make Z rotation also. The same chalk piece, if I can keep the chalk piece cylinder axis parallel to the blackboard, I can create X translation, I can create Y translation, I can create perpendicular to the blackboard rotation, Z rotation, and along the chalk piece also I can make a rotation without lifting from the blackboard. That means what I want to say is, two translations and two rotations are possible for a cylinder. Similarly, if you keep parallel to y-axis, we have it two translations, two rotations. See, like that, depend upon the system, the degree of freedom is changing. That means what I want to say is, we have discussed 1 degree of freedom, we have explained the 2 degree of freedom system, I explained 3 degree of freedom system, I explained 4 degree of freedom system. Now let us say one more example. I am taking a chalk piece in the form of a cricket ball, like a sphere. In the shape of like cricket ball, I want to write something on a blackboard. With a sphere, I can make X translation, I can make Y translation, I cannot make Z translation because the condition is the chalk piece must and should in touch with the blackboard. See, because of that, Z translation is not possible. 2 translations and 3 rotations. What are the 3 rotations, sir? I can sphere, I can make X rotation, sphere I can make Y rotation, sphere I can make Z without lifting from the blackboard. That means the sphere touching with the blackboard, sphere shape of chalk piece touching with the blackboard consists of 5 degrees of freedom. 3 rotations and 2 translations. And the general spatial system is having 6 degrees of freedom. If I can throw a ball, it is having X translation, Y translation, Z translation, and not only translation, when it is translating, it is having X rotation with respect to X rotation, with respect to Y rotation, with respect to, because when I am throwing instant, starting instant to the final reaching instant, the occupation position is different. That's why all rotations, translations are taking place. 3 translations and 3 rotations. This is how generally we will try to consider the system. So that is how I can quote number of examples, the civil engineering examples as well as mechanical engineering examples. So with this introduction, let us go to the concepts. What are the concepts which we are considering? The first alternative is we can consider voice or the first alternative is sigma fx0, that is basically sigma fy0, not yx, it is y. Sigma mo or m, that is over z axis, or mz0. That is the first, this is the two-dimensional system, first time consider. In a two-dimensional system, generally you have 3 degrees of freedom. In a general planar case, the two-dimensional. Sigma fx0, sigma fy0, about x, that is actually not x, it is y. Fy0 and m origin or z axis 0. That is one combination of, that is generalized equations, equilibrium equation, because we have 3 degrees of freedom. When I am writing a blackboard with a chalk piece, I have x translation, y translation. I have a z rotation. That's why two translation equation, two rotation equation. I am assuming that the system is in equilibrium. By assuming system is in equilibrium, I am considering two translation equation and one rotation equation. That's why those are the 3 equations. Sigma fx0, sigma f, summation of forces in x direction 0. The summation of forces in y direction 0. The summation of the moments about z axis 0. Now let us come to the other alternative, second alternative. Not only like this, sometimes you can make fx0 or fy0 one equation, either only one translation, not two translation. I am considering one translation, two rotations. Sometimes this is also possible in the practical cases. But only here one condition is, when you want to use a second alternative, the points A and must and should be on a line, not on a line. Not lie on a line. Then it is not valid. That is one condition you have to take about that. Not on a line perpendicular to the direction of summation of the forces. Once again I am repeating, if you want to apply the first alternative, there are no conditions. But the second alternative, if you want to apply, the points A and B must and should not be not on a line, lie on a line perpendicular to the direction of summation of forces. By fulfilling this condition, you can apply one translation equation, two rotation equation. The third alternative is summation of moment about x axis 0, y axis 0 and z axis 0. This equation can be used condition that the point AB is here. This alternative can be used on condition that point ABC do not lie on the same straight line. Earlier also A and B must not lie in a line perpendicular to the direction of summation of forces. But here also the prerequisite condition to use this alternative is, see, this is sometimes they will ask in the GATE examination, what is the difference between the three alternatives. The first is it is applicable for all cases, any case you can consider. If I want to apply second alternative, A and B must not lie on a line perpendicular to the direction of summation of force. Third alternative is ABC do not lie on the same straight line. See, by fulfilling these conditions, we can write the equilibrium equations. So this is how generally we will consider the equilibrium equations. From the GATE point of view also, they may ask some questions on this analogy. So this is how generally we will consider the system. Now let us come to this is one thing which I already explained. Entire mechanics is we will try to analyze with the Newton's laws of motion. Whether it is statics or dynamics. See, the first law is already explained when I am discussing the equilibrium equation. If you consider particle or a rigid body, particle is a dimensionless object and the body is a rigid body concept. A particle of originally at rest or moving in a straight line with a constant velocity tends to remain in the state provided the particle is not subjected to any unbalanced force, any resultant force. That means every body in the state of rest or maybe uniform motion unless there is no external force acting on a body. Suppose I am putting a chalk piece on a plane surface, it is always at rest. The same, I am not applying any unbalanced force. Only I am putting chalk piece on the plane surface, like on a table, flat table. It is at rest. Every body in the state of rest. Or maybe uniform motion. That means the same chalk piece now instead of flat surface, flat table, I am keeping an inclined table. Now the body is moving, sliding, rotating. Rotation or maybe translate. That is what is called the constant velocity. The linear velocity is, or maybe angular velocity, whatever it may depend upon the type of degree of freedom. See, that is what, that is not the meaning of the system agent dynamics. It is in a motion, but it is a uniform motion. That is also in static condition. It is an equilibrium constant. There is no, I am not applying any unbalanced force. No acceleration, that's all. See, the first law contains the principle of equilibrium of forces. That is the concern in statics. This law also gives an idea of what is the law of inertia. We don't apply the concept of inertias. What is the law of inertia? We try to analyze. So this is called the Newton's the first law equation. First law contains the principle of equilibrium of forces with respect to statics. It mainly, this law, another name is called law. What is inertia is defined, that's all. Not application of any inertia force. I given a figure here. Suppose if you can see F1, F2, F3 acting on a body moving with a constant velocity. There are three forces acting on a rigid body or a particle. If you can draw a polygon, it is what is called, if you can, a concurrent system with three forces must and should be in equilibrium. That is the condition. If you draw a polygon F1, F2, F3, because we know the magnitude and direction of the three forces, that is an assumption. If you draw a free body diagram, the polygon will be closed. So then we can say that the system is in equilibrium. But in general, concurrent system with three forces must and should be in equilibrium with three forces. F1, F2 and F3. Okay. Now let us go to the second law. Second law deals with purely dynamics. There is no question of statics here. A particle of mass m acted upon by unbalanced force F experiences an acceleration that has or a rate of change of momentum. The force and a magnitude that is directly proportional. Acceleration and force. Proportional with it. When there is a proportionality, there should be a constant, m is a constant. That is F and A should move in the same direction. Then it is proportional. Force is proportional to the accelerated motion, acceleration. When there is a proportional, there should be constant, m is constant here. Suppose a satellite, when you are launching, when it is reaching at some level, remove the mass. Their mass is not constant. So that's why here the assumption is the mass must and should be constant. So that's why in dynamics, because if you see the earlier statics, some of the force is equal to 0, some of the moments is equal to 0. But in dynamic case, some of the forces is equal to mass into acceleration, some of the moments equal to, instead of mass, a mass moment of inertia, I, into instead of linear acceleration, it is angular acceleration. The same equation will try to modify like this. That is that is what is the difference between the static problems and dynamic problems. Okay. In statics, summation of the force is 0, summation of the moment 0. In dynamics, summation of the force is equal to, instead of 0, now there is a resultant force, there should be an acceleration. That's why mass into acceleration for translation degree of freedom. For rotational degree of freedom, some of the moments, instead of F is equal to ma, I is equal to, the moments is equal to alpha, torque is equal to I into alpha. Some of the torque, some of the moments is equal to mass moment of inertia into angular acceleration. Some of the force is equal to mass into linear acceleration. This is how we will consider it. That means what I want to finally conclude is first law deals with the static problems only. Second law deals with purely dynamics problems. That is the analogy. That's why the entire the engineering mechanics or any static or dynamic problem will try to analyze with Newton's three laws of motion. So that's why all of you have to understand that is the importance of Newton's laws. Sometimes we will modify Newton's laws. F is equal to ma can be modified in the form of, we will see that part in dynamics, because Newton's second law is also defined as rate of change of momentum. That means instead of F is equal to ma, F is equal to mv, mass into velocity, or m into dv by dt. M into, because the acceleration is dv by dt. The dt part, if you multiply both sides, f dt is equal to m dv. If you integrate, you will get the impulse moment equation. M is a momentum, impulse is force into dt. Integral if you take both sides. See, that is how you can convert the equation. Similarly, the F is equal to ma, you can convert the energy equation also. Like half mv square. Kinetic energy. See, that means it is a modification of Newton's second law or a D'Alembert's principle. When the problem is in dynamics, if you want to, it is not an equilibrium. If you want to convert an equilibrium, that equilibrium we will call as a dynamic equilibrium. That is what is called the D'Alembert's principle. We will see these concepts when we are discussing the dynamics. But at this stage, I want to clarify what are the principles which we are going to apply between the static cases and dynamic case. Static case, Newton's first law. That is the meaning of that is every body in the state of rest or maybe uniform motion unless there is no external force acting on a body. That means the velocity may be zero, velocity may be constant, there is no acceleration. That type of system we are considering as an equilibrium. It is in static condition. There is no question of dynamics. Second law deals with purely dynamics. It can be solved F is equal to ma, or force is equal to proportional to acceleration. It can be solved moment impulse, or it can be solved the energy equation. That is the crux of the problem. In a dynamic, in dynamics, in order to use these three laws, we should know, depend upon the data given in the problem, they don't mention use the Newton's second law, or you can use the work energy, or you can use moment impulse. You have to decide what principle have you apply to solve this problem out of three. See, that's why there are more alternatives. Compared with the statics is easy. But dynamics, you have to decide some of these things. Not only based on input data, whether I have to solve with Newton's second law, that is F is equal to ma, or momentum equation, or impulse, the momentum impulse equation, or a work energy equation. That is we have to define. See, whereas the third law deals with, you know very well, this is what we are doing with your brother, sister, parents at house. For every action, there is always a reaction. Even a rigid body, when you are removing from the all surroundings, we will apply active forces and reactive force. That is, the Newton's third law is always valid. Two particle, like a collinear system, two equal opposite. That is the best example for a tug of war. Okay. This way can be applied for static as well as dynamic problems. As for third law is concerned, always occur in pairs, equal and opposite, active and reactive force. Whenever there is action, there is a reaction. So this is how we try to analyze the system. Newton's the three laws of motion, the first, second, and third laws. I hope you got the clarity, because this is very important. With the entire engineering mechanics, always we are moving with Newton's three laws. We are solving problems with Newton's three laws. If you are reading another equation, that is also simple modification of Newton's three laws. That much weightage is there for your Newton's three laws of motion. So with this introduction of four principles, now let us consider this problem. I already explained to you. It is a civil engineering. Let us consider a body. Here one point I want to say, there are types of loads, type of beams, types of supports as for beams are concerned. Just now I explained the difference between a bar, beam, truss and frame. Bar is an axial member like tensile and compressive, which we are using in trusses and one-dimensional bars. Whereas a beam is a two-dimensional member, we are having a shear force and bending moment, 2 degree of freedom, one translation, one rotation. Whereas frame is having two-dimensional frame is having, three-dimensional frame is also there, that is having 6 degree of freedom, 3 translation, 3. But two-dimensional frame is having 2 translation, X translation, Y translation and Z rotation. Okay. Now let us consider, that is what is called the bar, beam, truss and frame difference. 2-dimensional I explained. Same thing is valid for 3-dimensional also. Analogy is same, but degree of freedom is dependent upon the planar and spatial you define. Now, types of loads are concerned, yesterday I already mentioned, it can be a concentrated or point load, or it can be a distributed load, linearly varying load, quadratically varying load, cubically varying load, quadrically varying load, quintically varying load, third order, fourth order, fifth order, nth order we can consider. But it is a distributed load. Either it can be a concentrated load or a point load, or it can be a distributed load, or it can be a moment or a couple. See, that's why there are 3 types of loads. As for load or a force are concerned, that is the input load or loads applied. The beams are 6 types of beams. Statically determined beams, statically indeterminate beams. The difference is, the determinant beams, the number of equilibrium equations are sufficient to solve the problem, the necessary conditions. Whereas indeterminate beams, the equilibrium equations are not sufficient. That's what. That is, equation may be more than the unknowns, unknowns may be more than the equation. Where we need other equations other than this. See, that's why those are called statically indeterminate. We cannot solve unless without the help of some other equations. Now, out of 6 beams, 3 are statically determinate beams, 3 are statically indeterminate beams. For mechanical and civil engineering is very, very important, because in our problems, engineering mechanics problems, we will consider all types of beams. Mostly we will confine to statically determinate beams. That is again a limitation. Because as you go on the higher courses, you will study statically indeterminate. But in mechanics syllabus point of view, we will confine to determinate. Determinate beams are cantilever beam, simply supported beam, overhang beam. Maybe one side overhang or 2 sides. When you are doing a swimming, if you jump from the flat, it is what is called the overhang beam. That is a simply supported, overhang and cantilever. Whereas indeterminate beams are proper cantilever beam, overhang beam, and not overhang, proper cantilever, continuous beam and fixed beam. With the overhang nature, if you are continuous beam can be overhang. That is what I want to mention. These 3 are called the statically indeterminate beams. Once again I am repeating, proper cantilever, fixed beam and continuous beam. Like railway track is a continuous beam. In some other bridges we are using a proper nature and fixed supports. Now that is called the 6 types of beam. 3 types of loads, 6 types of beams and supports. These are the boundary conditions. See, there are generally we are using 3 types of support. In all 6 beams, cantilever one end is fixed, the other end is free. Simply supported, one end is a roller support, the other end is a pin or a hinge joint. Fixed beam is both ends are fixed. Then whatever it may be, but finally there are 3 types of support. It can be a roller support, it can be a hinge or a pin support, or it can be a fixed support. Each support, what is the degree of freedom here represented? The roller support is having only one unknown. Roller is means on cylinder rolling on this. Out of we have to get 3 degree of freedom. Rotation is possible. About that is a cylinder is one axis. The translation along the beam is possible. Only not possible is perpendicular to the roller. That's why one reaction is an unknown. F is an unknown. Similarly, the pin is having only rotation, no question of translation. That's why one rotation is possible. That is I am not keeping as an unknown. It is a known quantity. The unknowns are X translation and Y translation. Then fixed support, we are not allowing anything. All are unknowns. Fx, Fy and jet rotation. All 3 are unknowns. And these are called the fixed beam. And the support reactions can be considered. These are the 3 types. In any case, we are using always the 3 supports. It may be roller support. It is only one unknown, vertical reaction. It can be hinge or pin. It is having 2 unknowns, Fx and Fy. That means we need 2 equations. That point is concerned. If you have another roller support, like that, you can combine all unknowns. If you have both ends fixed, 3 plus 3, 6 unknowns. That's why, see the simple logic. Why the fixed beam is a statically indeterminate beam? The reason is, a beam consists of one hinge and one roller support. So let us say, a roller support is a vertical reaction and hinge support is the x-axis and y-axis. 2 translation. Total as a system, we have 3 unknowns. We have 3 equations because it is a planar. I am considering a 2-dimensional. We have 3 equations, 3 unknowns. That's why the beam is called the statically indeterminate beam. Whereas a fixed support, if both ends are fixed, that is the left side as well as the right side. 3 unknowns on left and 3 unknowns on right. 3 unknowns on left and 3 unknowns on right side. Total 6 degree of freedom. And we have three equations. That's why 3 equations, 6 unknowns, the indeterminacy is there. That beam is called the static. See, like that we can consider the proper cantilever and overhang, that is the simply supported overhang as well as the continuous beam. We can try to do like this. That is very, very important. The rigid body equilibrium deals with the 3 concepts. Once again, I am repeating. One is types of loads, types of supports, and types of beams also, whether it is a 2D or a 3D. The truss and frames are mostly we consider 1-dimensional structures. Beam and frames are we are considering 2D and 3D. That is what they are. See, the truss and what are the limitations of generalizing names. Now let us come to the, just now yesterday we have discussed the 4 systems. Different 4 systems. Now if we can see here, simple example yesterday we have considered. First is coplanar or non-coplanar. Here this is a system, these all are coplanar cases. I am assuming that all forces are lying in a single plane. That is what is the condition. A coplanar system. Whether you are considering a 3 forces or 4 forces or 5 forces or 6 forces, all are in the same plane, single plane. See, that is what we are considering as the coplanar system. In that we have 4 types. Yesterday we have discussed. The left, first and second column we have discussed yesterday. How to do what type of system we are calling as the collinear. Here, the collinear is, let us say 3 forces, F1, F2, F3. Whatever may be the direction, if all are acting along the same line of action, they are called the collinear force. That means here, if you can see, when the force acting in all one direction, there is no moment, because no distance between the, if you take any point along the line of action of the forces, you don't get the moment. But if you want to take any other point, now if you can see the independent equations, sigma summation of the forces, I am taking axis as along that, I am taking sum of the force equal to 0. Let us say tug of war. The persons, one group of persons pulling the rope in one direction, another group. That is the best example of the collinear forces. Then concurrent forces. The earlier previous slides are explained when three forces are acting on a part, intersecting at one point, it must and should be an equilibrium. Because here the unknowns are I given a magnitude and directions of all three forces. Only the resultant force I want to calculate that magnitude and direction. If it is there, if it is not there, 0. Here I am assuming the body in equilibrium. So that's why there is no resultant force. The sum of the force in x direction 0, sum of the force in y direction 0. The diagram which I represented only three forces. It must and should be an equilibrium. But if four forces are there, it may be an equilibrium or it may not be an equilibrium. In that case, what we have to do, sum of the force x is equal to 0. If it is 0 left hand side and right hand side, then we can say that the system is an equilibrium. If it is not 0, then we can say that the system is not an equilibrium. F1, F2, F3 and F4. It is what is called the concurrent force system. Now let us come to the parallel forces. F1, F2, F3, F4. Like that, like parallel forces are unlike. Here, first F1, F2 is an unlike. If you take F2, F3, it is a like parallel force. Take F1, F4 again like. If you take F3, F4 is unlike. See, like that, the parallel force can be a like or unlike. Here, because all forces are not in the same line, that's why moments are modularity is there. Some of the force 0, some of the moment 0. If we see the two persons, this is what we are seeing in parks, etc. When children are playing. This is the best example of the parallel force system. Now the general case is a non-concurrent or a non-parallel force. That is what the meaning. No question of collinearity, all forces are not acting in the same line. The general case is sum of the force 0, sum of the moment 0. Effect 0, Fy 0, and sum of the moment about Zx also 0. So this is how generally we will try to consider the problem. Fx 0, Fy 0 and moment 0. A person is want to climb down on a ladder. If you can consider the two reactions at the two ends, the weight of the person, if you can consider. If you want, you can include ladder weight also. Most of the times when they compare with the person standing on weight is negligible as compared with the ladder weight. So because of that reason, we will, this is what is called the non-concurrent and non-parallel force systems. Where here we have three unknowns. Two translations are there, one rotation is also there. That is a generalized case. See, this is what is called the two-dimensional system. I hope you will get the clarity from this slide. I given type of force system and see all things. These are the things what we have to. These are the things what we have to mention here. For every problem, you have to mention these four analogies. What type of force system it is? Is it a collinear, concurrent, parallel, or non-generalized case? Non-concurrent, that is concurrent. Generalized case, it is not a concurrent, not a parallel. In a two-dimensional only. All are what I am discussing, it is in a 2D. That is the assumption I am starting this from. So that's why if it is a collinear, you have only one equation. That is what is the piston cylinder mechanism or a tug of war or a bar or a truss. These are the example of a one-dimensional problems. That means for every system, what type of force system you have to define. You have to draw a free body diagram, then apply equilibrium equations by specifying the type of system. So this is how generally we try to analyze the system. Then the concurrent, if it is all forces are intersecting at one point, then parallel, then general case of force system. Okay. See, these are the things what we are doing in analysis of two-dimensional problems. So now let us go to the three-dimensional problems. If the categories of equilibrium equation in 3D. So now this I am introducing 3D here. Concurrent at a point. See, it is a basically here assumption in 3 dimension is it is not a coplanar system. It is a non-coplanar system. Non-coplanar means not in one plane. Any two forces may say a table having 4 reactions, weights, etc. All are acting in different planes. See, this is what we are considering as the non-coplanar systems. In all these cases, we are assuming that the equilibrium in 3-dimensional, if you want to analyze for a non-coplanar system, it is having again one or two are indirectly both are same, but here the difference is all are intersecting in one point, all are intersecting in on a line, not a point. This is sometimes in civil and mechanical engineering problem we come across these type of cases. Like an unbalanced forces on a shaft, a number of components are rotating. In that case, the second analogy will come into the picture. In a single plane, all are unbalanced taking place, that is the first case. Like that. We will consider both first and two are indirectly the concept is same, but one is intersecting at a point and another is intersecting along the line. But all are basically XYZ means X direction there is a translation and rotation, Y direction there is a translation and rotation, Z direction there is a translation and rotation. Concurrent at a point, concurrent with a line, parallel, general case. Parallel and general case of forces. Fx0, Fy0, Fz0, moment about x-axis 0, moment about y-axis 0, moment about z-axis 0. So this is how we will try to analyze the system. Now let us take the first case, concurrent forces intersecting at a point. In that case, see, all three are translation equation, there is no moment, that is the difference. Suppose concurrent with a line. Here, because all are intersecting at along the x-axis, that's why there is no moment about, if you take about x-axis, there is no perpendicular distance. And about my and mz there are moments. That means when it is intersecting along the line, the number of equations required are 5. You require maximum, your available equations are 6, but here we are using 5 equations. Whereas concurrent at a point, available equations are 6, but again we are using 3 equations. So this is how generally we try to apply the equations for the different systems. The 4 cases which we are concurrent at a point, concurrent that is intersecting at a point, concurrent intersecting along a line, and parallel and general case forces. That means non-concurrent and non-parallel forces. See, these are the 4 analogies generally we will try to consider for any system. Either all are intersecting at a particular point or all are intersecting along the line, or it can be a parallel force system or it can be a general force system. The generalized case we can apply all 6 equations. That is a non-concurrent, non-parallel force system. Fx0, Fy0, Fz0, moment about x0, moment about y0, moment about z0. And parallel forces are cases because all are parallel, some perpendicular distance is there, If you take My, Mz perpendicular distance, if Mj, Mx, there is no perpendicular, that's why the equation is not valid. Because all are acting in single axis, x-axis, Fx0. Like that, depend upon the type of system, we can apply the equations. Available are 6, but we are applying only 3. That is not the meaning of it is a two-dimensional. That is one thing you have to understand. That is F1, F2, F3, F4, etc. acting in along one plane, it will go to the coplanar system, but it is not a coplanar. That is the first thing. The table is the best example. Similarly, that is a free body diagram we can represent. A generalized case is non-parallel, non-concurrent with a non-coplanar system. This is how generally we will try to consider. So now this is what is now I am coming consolidating the things for equations of equilibrium. Sigma Fx0, sigma m0, Fx0, Fy0, moment 0 for a 2D. See the top equations of equilibrium are 2D. What is the meaning of that is? It's summation of forces, algebraic sum of the x component of all forces on the body 0. Algebraic sum of the y component of all forces acting on a body 0. Algebraic sum of the couples about the point are 0. So this is how we can consider the two-dimensional problem. Two-dimensional means it is a coplanar system by default. All forces are acting in a single plane. All forces and moments. Now if you can see here, equation in 3D. In 3D, we can consider top part is 3D and bottom part is 2D. I am comparing the both. In three-dimensional generalized case, summation of force in x direction 0, summation of force in y direction 0, summation of force in z direction 0. And similarly, moment about x axis 0, moment about y axis 0, moment about z axis 0. 3 translation, 3 rotation. The bottom part is like a structured truss or a beam. The left part is a truss, right part is a beam, two-dimensional beam. That is one the truss structure. The truss is one-dimensional. If you want to resolve two-dimensional like x-axis, y-axis, that is possible. But member is one-dimensional. That is what is the two-dimensional truss means. Each member is one-dimensional. But when you are representing in as a system, it will resolve x and y axis. That's why we are considering as two-dimensional. Fx0, Fy0, moment 0. Because it is a two-dimensional, we have 3 equations. Three-dimensional, we have 6 equations. See the golden rule is anything and everything that does not move in this world is known as a perpetual equilibrium. Suppose I am sitting in a room, the room is fixed and the table is there, it is fixed. So as far as the table is concerned, it is an equilibrium. It is because not moving. Or there is no unbalanced force acting. See, this is how generally we will try to consider the golden rule, the perpetual equilibrium. 3, that means whether it is a 3D or a 2D, whatever it may be. Now the same analogy, once again I am repeating for a brush up your knowledge. I am combining. The necessary and sufficient conditions are summation of forces 0, summation of moment 0. If it is a two-dimensional, 2 force equation, 1 moment equation. If it is a three-dimensional, 3 force equations and 3 moment equations. The moment equation can be determined about any point. The point where the maximum number of unknown forces are present, simplify the solution. That is by experience you can consider that. Once again I am repeating. The point where the maximum number of unknown forces are present, simplify the solution. That means in your equation, when you are getting a moment equation, if you take a point in such a way that if I can take a point, maximum number of unknowns will not come into the picture in the equation. That is the way you can get easy solution. Nothing wrong, you can take any point. But in GATE and other exams point of view, because time is also a factor. You have to use this. These type of tricks can be used. You can get solution very fast. Okay. See, this is what is called the summation of force at 0, moment 0, 6 equations for 3D problem, 2 equations for same thing. A rigid body I am representing in a non-coplanar system. The previous slide only I am representing in other way. We have 3 moments, 3 translations. Total 6 equations. You will get 3 translation equation and 3 rotation equation. See, because of that, what is happening is we will write the 6 equations. We can solve 6 unknowns. We cannot solve more than 6 unknowns. Unknown can be a magnitude and direction. Force, magnitude, and direction. If you want to solve unknown, suppose F4 magnitude is given, direction is not. System is an equilibrium, but some unknowns you have to find out. To keep an equilibrium, what is the value of F4 magnitude? To keep an equilibrium, what is the F1 direction? Like that, sometimes give the problem. See, in that case, what we have to do, we will apply 6 equations with 6 unknowns. Fx0, Fy0, Fz0, moment about xx0, moment about yx0, moment about zx0, and get the solution. Now let us take one or two examples of the problems you can easily understand. Here I am considering a person. See the problem. First thing is what type of force system. There is a coplanar or non-coplanar, 2D or a 3D we have to define. Then draw the free body diagram. Then we have to apply the equilibrium equations. Before applying the free body diagram, what we have to do is you have to remove all the surroundings, apply active and reactive forces. Here a man rises a 10 kg. The problem, if you want to note down, a man rises a 10 kg joist. Please note down the problem. A man rises 10 kg joist up length 4 meter by pulling on a rope. Find the tension in the rope. That is unknown is asked. And the reaction at point A. Reaction at point A. I already mentioned first you have to create a free body diagrams of a joist by applying all active and reactive forces. Note that the joist consists of 3 force body. One is the tension in the rope, second one is the weight, the third is the reactive forces or active force at point A. The reactive forces we have to consider. Reaction at A. There are 3 forces you have to consider. I already mentioned one thumb rule, whenever the 3 forces must be a concurrent force system to keep for static equilibrium. Because here I want to say that the system is in equilibrium, otherwise the unbalanced forces are acting. Therefore, the reaction R must and should pass through the intersection of lines of action of the weight and the rope forces. Determine the direction of the resultant force R. That is what at point A. Utilize a force triangle to determine the magnitude and reaction force. Utilize the force triangle to determine the magnitude of the reaction force R. Now I am drawing a free body diagram. us see. The weight is acting downwards. The tension in the rope is, because always weight is gravity force acting downwards, that is fixed. The tension of the rope is along the rope, that is T. Now where weight and rope tension are intersecting, that is the point the reactive force also must and should pass. It is something like a roller type at the contact point. It is like a cylindrical surface, a roller. That's why only one reaction. If you consider that is R is a reactive force, and the tension in the rope is again active and reactive forces, which we have to consider unknown, and weight is a downwards. It is a given. 10 kg is given, 1 kg is 9.81 newtons. That's why it is 98.1 newton weight, because we are considering SI units. We have converted that. Create a free diagram of the jaws. This is what is the three forces. Must and should be concurrent, means they should intersect at one point. That's why. That means here, if you can see what I want to say is, how many unknowns here? There are three forces are acting: W, T, and R. Three magnitudes and three directions. Three forces, three magnitudes. The total 6 quantities. Out of 6, we can solve, because a concurrent force system, we can apply 2 equations only. This we already considered. Collinear, 1 equation. Concurrent, we can apply 2 equations. That means maximum 2 unknowns can be solved. In non-parallel, non-concurrent, we can apply 3 equations. See, because of that combination, what is the problem is here? All are intersecting at one point, that is satisfied. Accordingly, R direction is fixed. That means here, the W is concerned, we know the magnitude as well as we know the direction, which is acting downwards. That is the vertical axis. As for tension T is concerned, it is along the rope. The direction is known to you. Magnitude is unknown. The support reaction, the reaction direction is known to you, because it is intersecting, all the three are intersecting. The direction is known. The unknown is the magnitude of R. Out of 6 quantities, 3 magnitudes, 3 directions. Direction means it is an angle of inclination with respect to x-axis. That is alpha. Otherwise, we can find out these unknowns. Now let us apply, determine the direction of reaction force. AF is equal to, now if I can bottom, if you can see the angular representations of all as per the given dimensions. F is a point I have taken along the x-axis, E is a point by drawing a vertical from C and G, passing through C and G, where touching E, and alpha is the inclination of AC. 45 degrees is given in the problem, that we are taking as the angle. Then other parameters are the data given, because the tension, if you can see the previous problem, the 2 angles are given. This is given 25, 45 given, this length is given, geometry. And the weight is given and length 4 meters. By taking that as an input, here see, the length is given 4 meters. This 45 degrees are given to you. Now by doing a geometry, what I am doing from C, I am drawing one vertical line. From C, I am drawing one horizontal line. By joining B and B, from passing B, I am drawing another vertical line where it is touching D. Okay. Now I am taking one triangle CBD, another triangle AAC, and this is what is called the rectangle EECDF, etc. And one more triangle ACB. By considering all this, first AF is horizontal component. AF is equal to this AB cos 45. That means length of AF is 2.828 meters. Similarly, the length of CD. CD is equal to AE. AE is this. AE into half AF by right angle triangle of AF is this. Is a midpoint. If we can measure. AE is equal to half AF. Because this is 45 degrees. If you can see, this is one triangle and this is another triangle. And this is 45 and this is 45. By considering this, or AE cos 45 or AB cos 45. Like that. See, now we can calculate what is the value of this one. Then AF is already 4 meters, 4 by. If you can analyze this is what the value. Then BD. BD is this value. That is CD. Cot opposite side by adjacent side. Cos 25. Cot 25. This by this. Tan 25 is opposite by adjacent side. Cot 25 this by this. So by considering that, we can find out the value of BD. Then the value of CE. CE is this. C is equal to BF by BD. BD is already known to you. BF is already calculated. By from these two, you can find out this is what is the AF is equal to. This is AF. And by considering that value 2.8 to 8, this is the AF value. By considering that, we can try to analyze finally the tan alpha, the direction of this reactive force along this direction with respect to this. This is the direction of the reactive force. By making an angle alpha, find out this. This is how simple geometry. You have to find out what is the direction of the resultant force. Even tension also, because this direction is given. If you can see here in the previous problem, the direction of the tensional force is given, only magnitude unknown. Now here the R part, the geometry, the direction is determined. The reactive force direction is determined. Now we have to find out the if you want to find out the unknown of forces also. Now let us go to the another problem. There is a beam problem where two weights are applying W1 and W2. W2 not W board weight as well as the mass, the M1 weight, and two reactive forces F1 and F2. One type of beam or a plank, a small board. That weight is mass into board of weight and into G, and M1 weight into G, that is at X distance. These are the dimensions are given. The moment you can take any point, because we are assuming that the system is in equilibrium. Moment or a torque location, you can consider convenient location, equilibrium at torque is 0 about every axis. Now if I can take about momentum, about weight, about that is any point, the choice is yours. I am taking here the moment equation about F1 point, choose an X point, that is the point I have taken. The weight W1 into X and weight then W board into L by 2, that is the midpoint distance. These are the two weights and other reactive force, because at F1 I am taking a moment point, that is 0, and like this we can apply the moment equation, clockwise moments and counterclockwise moment, because the sum of the moments is 0. Clock 1 is positive, other is negative, or otherwise you have to L if you move into left hand side. But if you can see the system here, W1 is given, W board is given. Magnitudes are given, directions are given. Only unknowns are F1, F2, but those are magnitudes are unknowns. Directions are known to you because there is a vertical upwards. F1 is acting upward, F2 is acting upward. See, because of that, both are directions are known, magnitudes are unknown. That is the reason why W1 into X is equal to W board into L by 2 is equal to F2 into L. That is the moment equation. Force equation is upward forces, downward forces. F1, F2 are upward forces. W1, W board is downwards. In these two equations, two unknowns. F1 is unknown, F2 is unknown. See, like that we can consider. This is one type of parallel force system in a coplanar. The previous one is concurrent. All are intersecting at one point. And this problem is a parallel forces. Only the data input if is given. This is the free body diagram for a particular beam. Beam means with some supports. I already directly drawn a free body diagram. By removing supports, I represented two reactions, F1 and F2. And weights are acting W1 and W board. And M1 and M2 are the forces. So this is how generally we'll consider the system into whenever the parallel forces. It can be alike or unlike, but here this is mostly an unlike parallel force system. Some are downward, some are upward forces. So which we are considering as the analyzing problem. So this one is a concurrent force system, concurrent, and this is a parallel force system. This is a parallel force. Now let us go to the another problem of rigid body. Earlier I had done equilibrium equation. Now if you want, you can solve the same problem, the previous problem, where I have determined the direction alpha, because that location is not given. From geometry I determined. Don't say that alpha is not an unknown. It is only from geometry we have determined alpha. Unknowns are two magnitudes, T and R. The magnitudes. Alpha from geometry we determined. That's why it is not an unknown. Okay. The magnitudes T and R is unknown. Now we can determine by applying equilibrium equation, that is sum of the force equal to 0, sum of the moments equal to 0. Or now you can use the triangular law of principle, Lamy's theorem. Anything that choice is yours, whichever is, you can apply any theorems, or you can apply polygon principles, or you can apply directly equilibrium equations, sigma fx 0, sigma fy 0, moment 0. So now this is what to see. The weight is given downwards, this problem. Weight is downwards. That means this is the equation, weight downwards. We know the magnitude and direction of weight. This is the downwards. We know the magnitude and direction. But as for R and as for T is concerned, we know direction only. We don't know the magnitudes. But one point we know the value. R is must and should be passing through this point. T must and should be passing through this point. Why? Because parallel to this, one point has to pass either this point and another point has to pass. Because that is how we are considering the analogy. Because weight is downwards acting, one has to pass like this, and has to pass that. Because of that reason, the weight to acting downwards, we know the magnitude and direction we represented. That vector, one end you can start with this line, another end you can start with where it is intersecting, that is a common point. That's how we can complete the polygon. Now parallel to this direction, we know the direction, we don't know the magnitude. Here we know the direction. Direction is known here, but only alpha is from geometry. These are all exercise to determine alpha, that's all, nothing more than that. Alpha is determined, this part, direction, because this alpha is given. With reference to this, what is this extra angle? That is the only what we have done here. See, the extra angle alpha, this plus this angle or total angle alpha is determined here. Direction is known, only magnitude is unknown. Indirectly, this is the location and this is the direction. The direction is known. And for tension is concerned, this is the direction. Magnitude is unknown. And as for weight is concerned, this is the direction and the weight is known. Magnitude is known. See, because of that, parallel to T, draw from this point, where it will intersect, we don't know. Parallel to R. Parallel to R means along this direction. Along this. Parallel to this, draw one more line. This is T, this is R. Where it is intersected, that is the point. Now it should be a closed polygon, downwards, then R, then T. Already this vector you represented with one scale, because 90.8.1 is in Newtons. With that scale you can measure, you can directly get. That is what is the polygon law, geometric, that is a graphical method. That is one way of, you can solve three ways. One is the graphical method, some polygon laws like parallelogram law, Lamy's theorem, triangle law principles, etc. Third is analytical equations like fx0, fy0 moment. With respect to the one scale you represented this vector, the same scale you measure this and this, directly get the values. That's all. The problem is solved. Another is, if you can use a geometry, this is a graphical method. If you can use a geometry, from the previous problem we know all the three angles, because this geometry is already measured from the figures. 110 degrees, 38.6, 31.4, because total 90 degrees. From that, if you, this is known, 90 minus this is 31.4. Similarly, this we determine, this is a vertical, because here already given these angles, accordingly find out. The three angles are known to you. By using this Lamy's theorem, you can apply. This force proportion divided by sine of that angle. The T divided by sine of 31.4 degrees is equal to R by opposite angle, R by sine 110, then 98.1 Newton, because I am units I am fixing, 98.1 Newton divided by opposite angle, sine 38.6. From this, unknowns are only two. This is one equation, this is another equation, these two one equation, these two another equation. We have two equations, two unknowns, and find out, and these are the values of tension magnitudes. That means in the problem, in a concurrent force system, we can solve only two unknowns. That is the one translation and that is two translations or one translation, one rotation, the choice is yours. Okay? But perfect three forces when it is a concurrent. More than that, we can consider sometimes three equations also. But in a three forces, it must and should be a concurrent. In that case, it must and should be an equilibrium. And we have to apply only two equations. That's why the two unknowns. One is that magnitude of T and another is magnitude of R. We can determine. So now let us consider some more problems where the free body diagrams. One is a ladder. The top one is a ladder where it is assumed that it is in a plane, coplanar system. Three forces are acting. One is a gravitational force, the weight of the ladder, self-weight. Weight of the ladder, reaction at the floor at point A as well as at the point B. RA and RB, that I am calling as RA is R1, RB is R2. Now again, the three forces must and should be like that. By condition considering in that case R, if it is a vertical wall, the horizontal reaction, horizontal wall, vertical reaction. By fixing like that also we can determine the three forces by keeping unknowns as per the equation we can determine. If the equilibrium, that is the concurrent system equation is not satisfying, then apply fx0, fy0, moment 0, etc. solve the problem. That is what is the upper part of the body, upper part. Then a body is moving in inclined plane, let us say. Now what we have to do, the body you have to remove, apply reactive force R, that is in between the inclined plane and the block. That is a given R. Assume that inclined plane is not there. So this is what I already represented, the remove all the surroundings. This is one thing you have to remove, apply tension, active and reactive forces. This is your weight is given to you. The problem is there is no T and there is no R. Right? That is the given problem. But free body on the same diagram I represented by removing all the surroundings. This has to be removed. This has to be removed. Now weight is acting downwards, gravity force. Between these two active and reactive forces, that is the reactive force R. Tension in the this particular wire is T. Okay. See, now we have to apply all the three are intersecting at one point, if you can see here. When it is intersecting, it should be three forces concurrent, it must and should be in equilibrium. You have to apply only two. Because when it is intersecting, all are intersecting point, if you take a moment, there is no moment equation. That's the meaning. That's why there is no sanity of the moment. Indirectly it is satisfying, but you don't get any unknowns. That's why fx0, fy0. Two translation equation. fx0. At the same concurrent, it is another type of curve, in inclined plane curve. In between friction is there, then fourth force is coming. In that case, this three force concept is, then you have to go for generalized case. Okay. So now in that case, because these two are, suppose fx0, fx is along this axis, fy is along this axis. I am resolving. Or you can resolve along this axis, along perpendicular. The choice is yours. There is no thumb rule you have to do, consider axis are like this. In any orientation, axis can be considered. But in this problem, as far these equations are concerned, I am considering this is one axis and this is another axis. fx0 and fy0. fx is, because see, if I draw one line, I extend this line. This is perpendicular to this and this is perpendicular to this. That's why the angle between these two is theta, and this line and this line, the angle is theta. Then W cos theta and W sin theta. This angle is theta. This is W cos theta and this is W sin theta. Because this angle is theta. This W cos theta is acting downwards, W sin theta is acting towards left with reference to this. This is right and this is left. Now x-axis consists of two forces, T and W sin theta. Both are acting opposite. So that's why sigma fx is along this axis T minus W sin theta. W is given to you, let us assume. Theta is given to you. These two are input. Unknowns are magnitude is known, direction is known. Okay, this direction is known because parallel to this. This direction is known because between this the theta. That is, direction is known and only magnitudes are unknown. Two unknowns can be easily solved with the two equations. Summation of force in y direction 0. Y direction means R and this is one component R. And R cos theta, because the fx0 is T minus W sin theta. This is W cos theta and this is W sin theta. Okay. W I am resolving along this axis and along this axis. Wait. If I want to resolve along the vertical axis, again the equation can be T also, this T. Also you have to resolve, R also have to resolve. See, like that we can determine the equations. One equation I have taken like this, another equation if you want you can take like this. Or you can take along this. Both ways are represented, but generally it is better either along this axis or along this axis or weight axis along this axis. See, by considering that combination, we have to consider here From solving, we'll get W cos theta. Okay, by solving the two equations, W and T and R. T is there, R is there. If we can solve that, we'll get two equations. See, this is the first part. Before going to the next, I will solve one or two problems. That part I will go a little bit fast. Now here, today what we explained are, what are the learning outcomes which we are going to get from the yesterday class and the today class, outcomes, learning outcomes. From this you have to get the course outcomes. Then program your mechanical or civil engineer. But from this topic, the learning outcomes are, what are the tricks we have to follow in the gate examination, where the momentum point can be considered. And today mostly we'll touch what are the equilibrium equations to represent in two-dimensional, three-dimensional. What are the different systems which we are considering to analyze civil engineering, mechanical engineering problem, like I seen in mechanical. Structures are concerned, bars, beams, truss and frames. And then we have considered some problems. Whenever you are considering any problem, first thing is what type of force system it is, and what type of free body diagram. Then what are the equations like concurrent, parallel. So now I will try to solve the closest friend of mine. Now I will go to the another problematic paper. It is, if you want, you can download. It is there in the internet also. But you cannot download it. This is the author is given. I will try to repeat the things. See, this is what the magnitude, as per force is concerned, magnitude, point of application, direction. This is the beam, one load, type of beam, type of support, a concentrated load or distributed load, uniformly distributed or linearly varying or quadratically varying, cubically varying load. The forces can be solved by using a parallelogram law, yesterday which we have discussed, or it can be, notes will be supplied to you, please go through. Then the free body diagram, suppose this body is there, remove the surroundings, apply active and reactive forces. As per this surface is concerned, this is the reactive force. As per this is concerned, this is the active and reactive forces. And similarly, this is the body connected with the rope, a spherical bar. This is the force and this is the reactive force as per this surface is concerned. Equal and opposite force on the string as well as equal and opposite force on this block also. Okay. And as far ball is concerned, again it is a concurrent force system. If you can see, this is the reactive force and this is the one force and this is the third force. Okay. Then let us see the block resting on a plane surface, the block resting on the curved surface. If the double is the block, if you can remove the surroundings, that is there is an active and reactive forces, R and R. One R is here, another R is here, the weight is acting downwards. And suppose if you can consider curved surface, at the contact point, there is an active and reactive forces. But here the point is, what is the difference between here and here is, here this body is having only X translation. This body is having, when it is moving on a curve, it is X translation as well as Y translation. That is the difference between the two analogies. It is only 1 degree of freedom, you can consider here it is 2D. But the free body diagram is like this. Weight acting downwards, vertical reaction upwards. Then draw the free body diagram for C. The weight acting, the problems can be only by giving input, unknowns can be solved. But free body diagram is very, very important. Now let us see the free body diagram of a 2 strings ropes connected with the weight W. The common point is C. Because why? Because it is a concurrent system. Weight acting downwards, this tension is acting in this direction, this tension is acting in this direction, intersecting at one point. This direction is known, this direction is known, the magnitude is unknown, magnitude is unknown. As far this is concerned, let us assume that weight is known, direction is known. The two unknowns you can easily solve. When you are talking moment about this point, there are no moments. That's why only X translation and Y translation. You find out. Or a graphical, represent a triangle, determine the unknowns. Or a Lamy's theorem. You can solve any method, the choice is yours. How fast you can do, by which method, the choice is. But gate examination point of view, either Lamy's theorem or FX-FI0 is better. Instead of graphical, it will take time. Parallel lines, you have to draw scale, you have to take, it will take time. So better to from gate point of view, either you can use the analytical method or you can use the geometrical method. That is a better. Now, let us take a spring. The weights generally measuring in the market consists of this simple method. The tension in the spring. This is not a rigid body, it is a flexible nature, but this is a rigid body. With reference to this, there is a tension. Instead of wire, we are using a spring. This is S, tension in the spring, weight W. Simple enough. Now, a body rolling on an inclined surface C. This is the reaction. This is the weight downwards, W. And the force also I am applying P with respect to horizontal. Now see, this is what it is. Because it is again a concurrent 3 forces. 1, 2, 3. All are intersecting at a common point. Okay. See, like the free body is very important. Next part is only you can apply any of these methods, either graphical method or a geometrical method or analytical method. But how best you are representing free body diagram, how fast you are representing, like in competitive examinations, is very, very important. That's what please all of you. Now let us come to the equilibrium of collinear forces. Suppose this is what the minus P plus P tension or a compression. If it is acting away, increase in length. If it is acting towards, this is what is the bar problem. The same bar with respect to certain orientation like 45 degrees, 30 degrees or even 0 degrees sometimes or 180 degrees. That is we are considering the truss. Truss we are considering orientation, bar without orientation. That's what. That means even at inclined 30 degree along that axis only we will take axis. That is where the orientation. If you take a orientation, it is a truss member. Without orientation, if you can consider either x-axis, y-axis, z-axis, is a bar. Both are one-dimensional structure. If you want, you can resolve 2D, 3D. But the member is a one-dimensional. As per the member is concerned. That we are going to discuss in the tomorrow class, the trusses. This I already explained yesterday, superposition principle. Please, if you want to note down this problem, a man of weight W, 712 newtons holds one end of the rope that passes over a pulley vertically above his head through a fixed rope, and to the other end of which is attached a weight W attached to a weight W, 534 newtons. Find the force with which the man's feet press against the floor. Find the force with which the man's feet press against the floor. Once again, I am repeating, a man of weight W, that is a man. Instead of block, assume that it is a man. A human being is standing. It is with a weight, holding a weight 712 newtons, one end of the rope, that passes over a fixed pulley vertically above the head. And to the other end of which is attached to a weight 530 newtons. Find the force with which the man's feet passes against the floor. See, let us assume that the tension in the rope, active and reactive forces, because here you have to draw the free body diagram of this body. This is one rigid body, and this is another. Man is also considered as a rigid. This is one body, two legs, let us say. Okay, this is the head. See, this is how the weight is holding 712 newtons. This is the tension in the rope. The same tension is valid because we are considering a frictionless. It is a conservative system. There is no gain or loss. And the tension in the string, because of this is the block, free body diagram. S is a tension and the weight is acting downwards. Because here man is resting, standing, that put the reactive force is also there, R, active and reactive, because he is pressing downwards. This is one more thing. Okay. Tension in the string, load attached to this tension is because there is frictionless. Here weight is given Q and here S is, as for this free body diagram is concerned, one downwards and then one on the both, if you can equate, S is equal to Q. Then in that case, S is equal to 5. That means this is known from this free body diagram. Remove and draw a pulley here, one force here, another force here. One is the Q534 and S. Here equal and opposite. With reference to this, S upward. With reference to this, S downwards. Now S is equal, if you can consider this, that is what the S value. Now applying a parallelogram law or any law of principle, W is one force, S is another force. What angle is pressing the feet by considering W and S, the two forces actually represented not in a line, that is what is the meaning. Resultant force W square S square 2WS cos, because the angle is 180 degrees. The parallel. The two sides. If you can apply, considering that this is what W minus R is equal to W minus S is already known to you. If I determine the R can be, direction is 178 newtons. Upwards and downwards, active and reactive force. See, this is how the problem can be solved, the first problem. Now let us come to the second problem. If you want to note down, a boat is moved uniformly. A boat is moved uniformly along a canal by two horses, P and Q. By two horses, P and Q. Pulling with forces, P is equal to 890 newtons and Q is equal to 1068 newtons. 1068 newtons, acting under an angle alpha is equal to 60 degrees. Acting under an angle alpha is equal to 60 degrees. Determine the magnitude of the resultant pull on the boat. Determine the magnitude of the resultant pull on the boat and the angles beta and gamma. And the angles beta and gamma. And the total angle alpha, that is beta plus gamma. Here if you can see the free body diagram is this is the horse, one horse direction. This is the second horse direction. Along a canal by two horses. Horse is one is on the left to the canal and another is right to the canal, and the boat is there pulling. Determine the magnitude of the resultant this force. That means here assuming that there is not an equilibrium, resultant force is asking. Now the simple is two forces are given, you can go with the analytical method, sigma fx0, sigma fy0, resultant force magnitude, resultant force direction. Because it is a two forces are intersecting, it is not collinear, it is a concurrent two forces. Now do I apply a parallelogram or analytical method or geometrical method? It is a graphical method, even parallelogram you can apply analytical equation. P is given 890 newtons. Q is given 1068 newtons. Alpha, total angle is given 60 degrees. In the problem, alpha is given 60 degrees. This is 60 degrees. Now P is given, Q is given, alpha input, free body diagram, input. This is the free body diagram. Alpha, gamma, alpha, beta, gamma, P, Q. And then I apply parallelogram, the resultant force R, magnitude. Direction is you can make tan gamma or tan beta. By using that we can determine the or using a Lami's theorem. Okay. These are the beta and gamma and the other angles 180 minus alpha, P pi minus alpha. You can find out the beta and gamma and the total angle alpha also. See, both Lami's theorem and parallelogram you can apply and find out the resultant force. Then this is already explained number of examples. I will skip this. Law of superposition. Now let us come to this problem. Please note down, this is very, very important. These are the types of problems generally come across in the GATE exam. Two spheres. With this we will stop. After completing this problem, we will stop today's lecture. Two spheres of weight P and Q. Two spheres of weight P and Q rest inside a hollow cylinder. Two spheres of weight P and Q rest inside a hollow cylinder, which is resting on a horizontal force. Draw the free body diagram of both the spheres together and separately. Which is resting on a hollow cylinder, which is resting on a horizontal force, means one obstruction is placed like this in a big cylinder. This is an obstruction. This is third obstruction. The base, like that is what the meaning. The two spheres P and Q are the spheres. Now we have to draw a free body diagram of this separately and this separately. As far this is concerned, this is the active force, is given force. Weights are not given. Weights are negligible. Only the two spheres P and weights are given, P and Q actually, two sphere weight. And this can be towards center point or from the center point downwards you can represent. And the active and reactive forces you have to consider here, and A, B and C and D. These are the contact. You remove all constraints. This is one constraint, this is another constraint as far this body is concerned, this sphere is concerned. As far this sphere is concerned, this is one and this is another. See, that's why RA, active and reactive forces, RC and RD, P and Q. But in between also one constraint when you are drawing separately. When you are drawing two spheres together, this is a free body diagram. See, when you are considering, now let us come to this one. So separately, because along this, if you can draw a red center to center, that is the direction. Along that, R1, R2. See, because it is a concurrent system, it is also a concurrent system, but only difference is it is three forces, it must and should be an equilibrium. And here, once it is in equilibrium, you can determine this. By that time, this is known. and this is also an equilibrium. So let us come to first consider this. We assume that P magnitude and directions is known to you downwards. It is a concurrent system. P magnitude is known to you, direction is known to you. Let us assume that P and Q are given. Direction is vertically downwards. RA direction is perpendicular to this. That is known to you, 90 degrees. And this, because joining of these two distances, once we know this is 90 by using this Pythagoras principle, this also we can determine what the angle. This direction is known to you. Okay. Magnitude and direction of P is known to you. This is known to, direction is known to you, and this direction is known to you. Unknown is magnitude of this and magnitude of this. R1 and RA. Two unknowns. By using Lami's theorem you can determine, that is geometry, or by using a triangular law principle you can determine, or by applying fx0, fy0, because there is no moment equation, because all are intersecting at the same point. That you can. Now let us come to this one. Because here, as far this is concerned, 4 forces, 1, 2, 3, 4. As far this is concerned, only 3, 1, 2, 3. This is active and reactive. R1 and R1 same actually. I am calling R2 means R1 is equal to R2, as far this is concerned. Okay, now this R1, once you solve this part, R1 is known to you. Now if this is concerned, R2. R2 is nothing but R1. This magnitude and direction is known to you. This magnitude, direction is known to you. This direction is known horizontal. This direction is known vertical. Unknowns are this magnitude and this magnitude. That means at any instant you can solve two unknowns in a concurrent system. Okay. This is a concurrent system and this is a concurrent system. But as for whole system is concerned, this is not a concurrent. It is a general case. But here, as for when you are drawing separately this body and this body, this is a concurrent system and this is a concurrent system. By considering this, we can solve this problem. Okay, here this magnitude and direction is known to you. This magnitude and direction is known to you because already you have solved this part. This is known to you at this stage. And this direction is known and this direction is known. Unknown is the magnitudes of RC and RP. Fx0, Fy0, Fx0, Fy0, find out. See, with this I will stop the lecture. Before closing the lecture, what are the things which we have considered today? What we have completed yesterday, we have reviewed once again. And what are the learning outcomes you are going to get? And what are the different tricks to be followed in the GATE examination? The thumb rule is how best you are representing a free body diagram first. Then the second part is whether I want to apply a graphical method or a geometrical method or analytical method to consider the system as an equilibrium. Okay. Then the other concepts which we have considered are when you are solving a two-dimensional problems, the generalized equations available are 3, but depend upon the system like 3 forces concurrent system or equilinear. The 3 can be reduced into 2 equations or 1 equation. Whereas in a spatial system, we can consider 6 equations, 3 translations and 3 rotations. That is what we are indirectly I am calling it the degree of freedom. That is one issue which we have discussed today. What is the degree of freedom problem which we are solving? You have to define what type of force system we are studying. Then free body diagram. Then what method we have to apply, whether it is a graphical method or a geometrical method or analytical method. So this is how we try to solve the engineering mechanics problems. Tomorrow I will continue some more problems and we will try to analyze the other part of statics part like trusses, center of mass and other principle of actual work. These are the some more topics which are left and with friction also. Till now we have not considered friction. How friction will be considered and what are the other forces that come into the picture when we are considering a friction. So this part we are going to discuss tomorrow and day after tomorrow. Once again, students, best of luck. If you have any questions or queries, please send a Google form. We will try to give a reply. Once again, I am thanking JNT Anantapur team for this wonderful arrangement. I hope you are getting, for online students, I hope you are getting everything clarity as the pictures are concerned, the delivery is concerned, audio and video part. If you have any queries regarding this, please communicate through Google Form. Thank you very much. Wonderful day and best of luck. Thank you. Have a nice day.